Welcome everyone to this webinar. My name is Griffith Kauser. I am a policy officer at the European Polar Board. We are the lead of Work Package 8, which is the Policy Communication and Dissemination Work Package for the SO-CHIC project. I'd like to remind everyone that this webinar is being recorded. The recording will be posted on the SO-CHIC YouTube channel. We are doing Work Package 6 for a series of webinar, which is part of deliverable 8.20 in the SO-CHIC project. And as a very brief introduction to the SO-CHIC project, this is an EU-funded Horizon 2020 project focused on measuring and understanding heat and carbon exchanges between the atmosphere and the Southern Ocean. It began in August 2018. It comprises 18 institutions, and SO-CHIC aims to add valuable data and understanding to the heat exchange and carbon exchange processes. So we are going to talk about Work Package 6 today, and for that we have 6 speakers. Work Package 6 is Variability and Trends of Heat, Carbon Uptake and Storage. The Work Package leaders for that are Professor Nicolas Gruber and Dr. Torsten Kanzow. Professor Gruber is a professor of environmental physics at the Department of Environmental Sciences at ETH Zurich, and I will introduce Professor Gruber now to talk more about the work package. I'm also putting a link to the SO-CHIC project should anyone want more information about that.
Okay, thanks a lot. Welcome everyone, and it's a great pleasure to introduce actually the Work Package 6, and I will also introduce the speakers in a minute. So Work Package 6, as indicated by Griffith, is about the variability and storage of heat and carbon in the Southern Ocean. And in this context, what we're trying to do is to look at both elements in a synergistic perspective. Today, we will be focusing primarily on the role of the Southern Ocean for the uptake of heat, but we will also touch upon the carbon every once in a while. I think this is a fantastic opportunity today, actually, to talk about the Southern Ocean, because yesterday, 50 years ago, this enigmatic picture was taken as the Apollo mission was heading towards the moon, and the astronauts were looking back at Earth and took this picture, probably the blue marble, maybe one of the images of the world that has been used the most, I think, anywhere in the time. And the fantastic element is a piece of that picture taken from the Earth is just that it demonstrates essentially the interactions between the key elements of the Earth system, and in particular, actually, what's fascinating also for us in the context of SO-CHIC, it actually shows the Southern Hemisphere. It's focused on the Southern Ocean between the Atlantic and the Pacific, with the African continent in the middle, and on the bottom you see Antarctica and the interactions of the clouds, the ice on Antarctic continent, the ocean underneath. And I would like to invite you actually to visit now a fantastic illustration that was just put up yesterday, put together by our German colleagues in Hamburg from DKZ and the Max Planck Institute for Meteorology, where actually they recreated that image on a supercomputer, and it's not only then a static image, it's actually a moving image, and you can see how clouds and the ocean interact with each other, and the ocean circulation underneath is changing. So it's a fantastic opportunity here to use this image to kind of jump right into the Southern Ocean in the context of our work package. As I said, we're focusing on the uptake of carbon and heat, and one of our main objectives is to quantify that uptake, but also looking at transport phenomena, looking at how the storage is actually changing through time and is affected by climate variability. The tools that we're using to address this question across scales, from looking at the Southern Ocean as a whole, all the way into the more focal regions of the Weddell Sea, are a combination of observations and models. And we're really focusing on the analysis observations, because most of the observations are taken from other work packages. We're actually more in the synthesis perspective of that, and looking at this question of carbon uptake and heat uptake. And a very particular sort of driving question in the whole thing is, how is actually this uptake and this transport and storage changing through time, and sort of contributing both to variability in the past and also will contribute to changes in the future. So this is what we're trying to do as a work package, and today we have the opportunity to get a glimpse in where we are in this work package. And I'm very honored to have actually 5 distinguished speakers following me now, starting with Torsten Kanzow, Krissy Reeve thereafter, Pedro Llanillo, and Mark Hague. And what we're going to do at the end of their presentations is we have a short panel discussion where we'll actually pose a question, lead into the Q&A that will be followed, and that will be moderated by Griffith after that. So this is the program for this afternoon. And now I have the honor and privilege to introduce our first speaker. Torsten Kanzow is a professor of physical oceanography at the Alfred Wegener Institute. He got his original degree, master's degree, from the University of Kiel in 2000, got the PhD in 2004, and thereafter did his first postdoc in Southampton between 2005 and 2007. Went back to Guiomar as a junior professor until 2013, where he moved actually to Bremen and the Alfred Wegener Institute, where he's now a professor and leader of the physical oceanography group. And I also asked everyone to sort of give me a little bit of a special element that they would that characterizes them. And one of the fun facts about Torsten is he has been so much out of sea that he probably can't count the number of days, but he was able to count the number of ships he was on, and at least 16 of them. So if you ever want to know something about your favorite ship, I'm sure Torsten could tell you a lot about individual components. And even more questionable in some sense is that he started out in tropics and ended up in the high seas of the Southern Ocean and also the Arctic. And of course, you can ask him later why he did choose so, I think, but it was a very good move indeed. So over to you, Torsten, for the first presentation on the Southern Ocean, and you will give sort of a first overview why the Southern Ocean matters and what we have learned so far. The floor is yours.
Okay, thank you very much. I hope you can understand me. Thanks a lot.
Yes, we can.
For the introduction. I'm just trying to find my presentation. I hope you can see it well.
Yes, we can.
Okay, so okay, I'll try to get rid of these videos, then I can better see. All right. Yeah, my task, I guess, is to fill you in on some, I guess, basic insights regarding the role of the Southern Ocean in terms of uptake, transport, and storage of heat and carbon. And that is then supposed to set the scene for the more topical presentations we're going to see from Mark, from Krissy, and from Pedro. And so, as a starting point, I think it's always good to remember the basic property distributions around the Antarctic continent in the Southern Ocean. What you see here is near surface temperature compiled from observations, and you can see this concentric distribution of temperature moving from, say, very low temperatures around the continent to high temperatures towards the subtropics. And many of the other, say, important fields, forcing fields and circulation fields, they are also very much characterized by kind of concentric angular distribution of properties. And what you see in the middle is basically the wind momentum input into the ocean. And the Southern Ocean is basically characterized by strong eastward winds in this belt, which you see in red. So you have decreasing winds if you move from South Africa towards the Southern Ocean, and then you have decreasing winds when you move towards the continent. And this pattern of zonal winds sets up one of the strongest circulation features in the world ocean, which is the Antarctic circumpolar current, which is an eastward drift of water masses around Antarctica. What it also does, and that can be seen when you move along a section from South Africa towards the coast of Antarctica, and look at the temperature field as a function of depth. Here's Antarctica, here's South Africa, here's Antarctica. You can see that these isotherms are tilted upwards as you move towards the Southern Ocean, with the cold waters being more and more closer to the surface. And that is related by this effect of the winds as well that I pointed out, in that, and now you need to be a little bit flexible because the Antarctic continent is on the right-hand side of the image, not on the left-hand side, is associated with this upwelling of water masses, the circumpolar deep water. And then some of this upwelled water masses being sucked up by the wind field is then transported northward again and across the ACC and finally subducted, so that these mode waters and intermediate waters are formed, which are very relevant for the uptake of carbon, for instance. Some of the waters upwelled around Antarctica actually managed to get onto the shelf regions around the Antarctic continent, where they are subject to strong cooling and to salt rejection by sea ice formation, and they form the densest water masses of the world ocean, which then move northward and get exported at depth. And it is this pattern of overturning and exposure to the atmosphere which makes the Southern Ocean so much active in air-sea fluxes of heat and carbon. And one way of readily seeing that is this presentation, or this result presented in the paper by Gruber et al., where they showed that there is a large-scale field of uptake of anthropogenic carbon or CO2 into the ocean around Antarctica, and that this is mainly ending up and feeding into these mode and intermediate waters, in which then those properties are transported northward. And indeed, about 40% of the carbon or excess carbon that has been taken up as a consequence of anthropogenic CO2 release in the atmosphere has been taken up by the Southern Ocean. And there are estimates that even up to 75% of the excess heat, so heat related to climate change in the past century or so, 75% of the uptake of the ocean may have been taken up by the Southern Ocean. So there's certainly a very strong role of the Southern Ocean. But it's not only these large scales that actually matter very much, it's also circulation patterns on much smaller scales that are very relevant in the climate system. And what you can see here is the Weddell gyre, which is a clockwise circulation feature south of the Antarctic circumpolar current in the Atlantic sector of the Southern Ocean. And in this regime, you have upwelling of these circumpolar deep waters. And you can see, for instance, the section on the right-hand side for temperature where this water sits close to the sea surface and is then being advected by a boundary current towards the shelf seas in the southern Weddell Sea. And in those, on the shelf seas, this water makes seasonal appearance on the shelf, and is basically, and there's a very delicate balance of wintertime cooling, advection, and other processes that decide about how much of that heat might actually be available for melting this massive ice shelf in the southern Weddell Sea. And then there are complex interactions between sea ice formation, the melting of the ice shelves, advection of these warmer waters that produce this very dense bottom water that cascades down the continental slope. And when we look at basically the exit of Weddell Sea, where these waters move out, we can see how strongly the properties from the inflow to the outflow have changed, with this very cold water sitting at the bottom associated with bottom intensified outflow. And so these two pathways, the pathway for converting these deep waters, these upper deep waters into intermediate waters, and the one converting those waters into the bottom waters, these make the Southern Ocean really a global connector of the circulation and also the uptake of heat and carbon. I'm not going to explain in detail what the subsequent presentations will be about. I just wanted to highlight that one of our collaborators in the project, Tilla Roy, is not present today, and I'm going to highlight one of her results in my talk, which is about projected trends in carbon in the Southern Ocean. But before coming to that, I would like to focus a little bit on temperature changes that have been observed. What you can see here again is one section across the Antarctic circumpolar current from south to north. And what is shown here is the multi-decadal temperature change in the upper ocean, roughly above 1,000 meters or so. That has been noted for a long time that this warming was ongoing. But the relevance of the study by Swart et al., who is also a collaborator in the SO-CHIC project, has found that basically this warming pattern is consistent with anthropogenic climate change using fingerprinting technique. And a very recent result is actually that this warming pattern has resulted in an acceleration of the Antarctic circumpolar current. So there's a feedback on the warming onto the circulation. What is also true and needs to be emphasized, it's not only the upper few 100 meters that are warming, but it's certainly the case that the Southern Ocean stands out in terms of its role in warming of the bottom waters. And what you can see here are decadal trends in the warming rate of waters below 4,000 meters from an IPCC report, not the most recent one, the one before. But I guess the statement is still very true that the Southern Ocean plays an outstanding role in uptake of heat in the deepest part of the ocean, where about 20% of the excess heat that the ocean has stored, the global ocean has stored, has been stored below 2,000 meters, and in this part, the Southern Ocean plays a decisive role. Now, coming back to the carbon and CO2 uptake question, coming back to the work and the study by or the review paper, I should better say, by Gruber et al. And we've seen the picture on the right-hand side before, the uptake pattern of anthropogenic CO2 and its subsequent storage in the ocean, in the Antarctic intermediate waters and the moat waters. But what is another important finding in the past years is that there is not a steady increase or a steady state in which the Southern Ocean sink of anthropogenic CO2 works, but there's strong decadal variability in the uptake of CO2. And this is what these time series show, which is basically the net anomalous air-sea flux of CO2. And we see that there has been a strong decrease in the efficiency or the uptake of CO2 in the 1990s, and that has been followed by a strong increase. And the mechanisms leading to the decreases and increases of air-sea fluxes of CO2 are not the same, and there also regional considerations matter a lot. But one statement is certainly true. and that is that the Southern Ocean, despite of the strong decadal variation, has remained a major ocean, a major sink for anthropogenic carbon. So that brings me to the last results slide. That's the result from Tilla Roy, who's our collaboration partner in the work package 6 of SO-CHIC. And she has looked into a model ensemble in the CMIP5 context of coupled climate models that have been exposed to a CO2 emission scenario, 1% per year atmospheric CO2 concentration increase. And Tilla Roy has looked at this model ensemble in a 140-year integration. And what they have found basically in this study is that under continuing climate change and under continuing increase of atmospheric CO2 level, the Southern Ocean continues to take up carbon. There's a strong carbon sink. And the beauty of this study is that they chose a water mass specific methodology in which they can assign the uptake and the processes to certain water masses. And it turns out that the Antarctic intermediate water and the moat waters remain the most important sinks for carbon or for anthropogenic carbon. But what is also true is that the Southern Ocean might be experiencing a reduction in the efficiency of CO2 uptake, but there the story is also not a simple one. It's complicated in that the moat waters, for instance, seem to be reducing their uptake efficiency by a reduction of their buffering capacity for CO2, whereas the Antarctic intermediate water, for instance, experiencing climate change due to circulation changes, which reduces the CO2 uptake. So understanding these exchanges and how they will evolve in the future is an unsolved issue, I would say, and say approaches like these, which are specific in terms of assigning processes and water masses, are a very good framework for understanding those. I think with having said that, I'd like to summarize. I hope I could convince you what you already knew, that the Southern Ocean plays an outstanding role in capturing excess heat and carbon, that the uptake and the transport of carbon are tightly coupled, that regional transport regimes matter a lot, that we have pronounced decadal variability to be understood, and we need to keep up scale resolving observations and efficient and modeling approaches in order to improve our understanding of the Southern Ocean's role in the climate system. Thank you.
Okay, Torsten, thanks a lot. If you could unshare your screen.
Yes.
Perfect. Thanks a lot again for the fantastic introduction. And now I would like to hand over to Krissy, who is also from the Alfred Wegener Institute. In terms of background, she got her master's degree in Southampton in 2010, did her PhD at the University of Bremen in 2018. And then also remained in Bremen, but joined AVI, as I understand correctly, as a postdoc. And since 2020, you are a PI on a big project in the Weddell Sea, and very much involved in getting a lot of observations, analyses, focusing on that region. This is also what you will be talking about in your presentation. In terms of a fun factor, you see already a little bit on the slides. She loved The Little Mermaid. I think that's I think a huge inspiration indeed to jump into the ocean. And maybe you can also, maybe in future generations, they will say, okay, well, as they will watch Avatar 2, which will come out next week, we'll have other people sort of jumping on the dragons in the near future. And she also became a mother last year, and I think so at the moment That's definitely something that keeps her busy as well. And so when she has good time, she loves to look at swirls in the coffee and the teapot. An English person, of course, more tea than coffee, and anything related to art. So this is something I believe that we can often really cherish and appreciate, the combination of art and science. And with that, I'd like to hand over to you, Krissy.
Hello, thank you very much for the lovely introduction. I will just share my screen. I hope you can hear me and see my screen.
Yes, we can. Shoot,
Lovely.
please.
Okay, so I'm going to focus in particular on the Weddell Gyre today. And I should say that I'm funded by the German research agency, this DFG here. So I'm collaborating closely with the SO-CHIC project. So thank you for having me. And my screen isn't responding. That's good. There we go. So first off, I just want to start with this lovely map. It's a Spillhouse projection. And what this really emphasizes is the fact that we have one global ocean. It's all connected. And the beating heart of this global ocean is Antarctica and the Southern Ocean that circulates Antarctica. This really joins up all the water masses that circulate this one global ocean. It's a really fascinating region. And I'm going to be focusing on that little black circle there, where the red lines, by the way, show the surface circulation of the global ocean, a general schematic, of course. And then the blue line shows the deep general circulation. And this region in the circle there is the Weddell Gyre. And already you should get an idea of the importance of this region in the fact that these lines connect. And this is something that Torsten's just been talking about. I'm going to dive into this region looking at observations. Now, how do we observe the Weddell Gyre region? I'm going to talk about Argo floats. That's my obsession. But it's not just the only observation out there, and we'll come up to that. So what is an Argo float? It is a float. And what we do is we chuck it over the side of the ship carefully, and then it sinks down to about 1,000 meters and then drifts in the current for 9 days. And then it sinks down to 2,000 meters. And as its surface returns to the surface, it measures pressure, temperature, salinity. Some of the newer floats have a lot fancier sensors on it, which is amazing. And then when it reaches the surface, it transmits this data to satellite. And then that satellite sends us an email with all this lovely data. And we get that every 10 days. And so we have thousands of these floats drifting in the global ocean right now. And in the Southern Ocean, what's really special about these floats is they have this sea ice sensing algorithm that predicts the likelihood that there's sea ice at the surface. Now, if there is sea ice at the surface, it saves that data, aborts mission to surface, and continues on its way until it's next able to surface and send that data to satellite. So thanks to Argo floats, we actually have coverage of the Southern Ocean, even in wintertime. And this is just to give you an idea of the drifts of these floats. They really get moving, especially in the Southern Ocean. And we can use this also to get the velocity of these floats as well. And this gives us so much information. It's a really cool data set. So I'm going to just focus on some of my results now using these Argo floats. The black dots in this figure show Argo float profiles from 2002 to 2016. The red lines show repeat ship transits. So already you can see just how much spatial coverage we get from these amazing Argo floats. And the color in this figure shows the subsurface temperature maximum. I'll come back to that. And the white contours show the horizontal circulation of the Weddell Gyre region. So where the lines are close together, the flow is really intense. And where the lines are spaced out, the flow is less intense. And so what we have here is this cyclonic gyre. That means the circulation is clockwise. And we have these two sub-gyre centers in the east and the west. And the west one is much weaker than the eastern one. So The reason why I'm looking at the subsurface temperature maximum is because this is how we define the core of the warm deep water that enters this Weddell Gyre region. This is the main heat source that feeds into this area. We really need to understand how much heat is actually getting into this area, especially because we have some of the largest ice shelves in that southwestern interior. So we have this warm deep water that enters the southern limb over in the east. And as it circulates this clockwise gyre system, it undergoes cooling. And you can see some of it circulates just west of the prime meridian there to circulate the eastern subgyre region. And some of it continues all the way to the west to circulate that much smaller western subgyre as well. So this gives us a feeling of how the water moves and also how the temperature is distributed. Well, we can put that information together and also take data from reanalysis data to look at the sort of vertical movement in the water column, and we can compute a heat budget. And this really gets us an impression of the mechanisms by which heat is distributed throughout the Weddell Gyre. And so that's what I did. And I'm not going to go into the nitty-gritty of it in the interests of time right now, but I'm just going to summarize in a schematic the main findings of how these mechanisms move this heat about. So we have those sort of not quite straight lines, and this indicates where the heat is carried along in the mean circulation. So we have that heat being carried into the southern limb of the Weddell Gyre, undergoing cooling as it goes along. We also have heat coming in across the northern boundary of the Weddell Gyre by mixing, horizontal mixing, and that's shown by these curly blue-red arrows here. And that heat gets carried away from the northern limb of the gyre through the horizontal advection. So the heat gets carried away in the mean circulation in the northern limb, and that's indicated by the blue to red arrow there. And in the center, we also have the mixing playing an important role in removing heat from the southern limb into the interior. Now that's really interesting because the interior is where we know upwelling is occurring. That's what Torsten was just talking about. And so the little blue circles there show a key removal of heat from the Weddell Gyre upwards through the thermocline by turbulent mixing. So we're starting to build up a picture of how heat gets moved about in the Weddell Gyre system. And this is purely from observation. So this is really useful. And it's also useful for modelers to get this input from observations as well. So what next? I'm just going to give you a little teaser about what I'm currently working on. So one of my obsessions is looking at the circulation of the Weddell Gyre and how it helps us to tell the story of the Weddell Gyre. In particular, what's going on in the east versus what's going on in the west. So if you look at that map there, the western Weddell Gyre is kind of sheltered. It's got landmass to the south and to the west. It's sort of got an open northern boundary through a lot of complex topography there. But over in the east, it's really open, it's really exposed, and it's highly dynamic. A lot is going on. It's also a region where we're really lacking data. We're really lacking observations in this highly dynamic region. So what I'm looking at the moment is long-term trends in surface nutrient concentrations along those red lines there, those repeat ship transects. And I'm comparing the east versus the west, and I'm trying to draw out what's going on in these regions and seeing if we can use the Weddell Gyre circulation to help answer these questions. And so this is my big question at the moment. Are the changes, the long-term trends in nutrients in the east versus the west, are they a result of different dynamical drivers dominating in these different sections? And that is really what I'm working on right now. So thank you very much for listening. I hope you've enjoyed.
Thanks a lot, Krissy, for a fantastic summary of your work and your enthusiasm working. You're definitely a great advocate for the Argo program. A wonderful observational network indeed, and a very powerful one. Okay, I'd like to go to the next speaker, which is Pedro Llanillo, also from Alfred Wegener Institute, but he only recently joined the Alfred Wegener Institute in the context of this project. In terms of background, he got his master's degree in East Anglia, and then moved to Barcelona, where he got his PhD in 2014, where he worked actually in the tropics on the oxygen minimum zones of the Pacific. Indeed, also very, very important region from a nutrient perspective. Then he moved to South America, where he was a postdoc between 2015 and 19 in Santiago de Chile, and also moved southward geographically in terms of the focal region from the tropics into the high latitudes, following Torsten's lead in that context. So you can ask both now why they would move. Why would you move from the tropics in the high latitudes? And then in 2020, he joined Alfred Wegener Institute, and very recently he actually joined in the SO-CHIC team. So really looking forward to your presentation, also focusing on the Weddell Sea. In terms of fun factors, I mean, he's a vivid outdoor person. He loves hiking up mountains, and it can't be the mountains can't be tall enough. The only challenge he has in life right now is that that Bremen is a bit on the flatlands, so you might sort of now discover essentially all the great hiking and outdoors activity that you can do at the boundary, and the very strongly moving boundary between land and ocean up there in northern Germany. So so this is a great change, and so I'm looking forward to your presentation on the changes in the Weddell Sea. Floor is yours, Peter.
So thank you very much for such a nice introduction. I will share my screen. I cannot share my screen, says host disabled participant screen sharing.
Should be fine now, sorry.
Yeah. Thank you. So right, can you see my screen?
Yes, we can. Please.
All right, perfect. Thank you. So hi everyone, my name is Pedro Llanillo, and as Nikki commented, I'm a postdoctoral researcher at the Alfred Wegener Institute here in Germany. And today I will be talking about how we want to combine observations and models to investigate the patterns of warming and cooling that have been observed in the Weddell Sea. So, yeah. Okay, so this is a brief outline of this presentation. I will very briefly introduce you about the physical context in the Weddell Sea, as has been nicely done by Torsten and Krissy already. Then I will discuss what do observations tell us about the Weddell Sea, mainly focusing in interannual changes in the dense water plume that flows along the slope, but also in the decadal trends which has been observed in the water masses in the interior of the Weddell Sea. From this, I will link to our scientific motivation for future work and how we want to investigate the drivers behind these changes with an ocean model which has been fit to observations. And I will finish this presentation with highlighting how our different modeling approaches complementing the second task of our package 6. So here you have mainly the western and central Weddell Sea, cyclonic circulation that Krissy was nicely introducing before is roughly depicted here by the dark blue arrows. We also have an important component here, which is the dense water plume that flows along the slope, depicted by the light blue arrows. And as you can see, it's mainly formed in specific locations of the Weddell Sea, like the Filsner Throat, but also some regions of Larsen Ice Shelf. This plume follows all the way along the slope and escapes the Weddell Sea at some specific passages, like the Orkney Passage, in the form of Antarctic bottom water, which you know fills the bottom of our oceans from that, and sets the start to the meridional overturning circulation in the southern hemisphere. The green line here represents the repeated hydrographic sections that have been accomplished along the years. We have one across the gyre and the other one on the right part of the map, this meridional section, which will be discussed briefly later in the light of observed changes and trends. In particular, this meridional section is depicted here, in which you can see the main water masses that compose the interior of the Weddell Gyre, the main subsurface water masses. So in the upper strata of the water column, we will have the warm deep water, which is the warmest of them. And in the bottom of the Weddell Sea, we find the Weddell Sea bottom water, which derives from this very dense shelf waters cascading down the slope and then mixing and entraining this warm deep water. And a fraction of this dense shelf water follows along the slope, the continental slope, and another fraction goes to fill the abyss of the Weddell Sea. And in between, we have a water mass that results from mixing of these two water masses, which is called the Weddell Sea deep water. So what do observations tell us about the Weddell Sea? Well, in this map, I'm showing you the location of different moorings, the red triangles that have been deployed by ABI across the continental slope in the eastern part of the Antarctic Peninsula, and also the yellow circles represent repeated CTD stations. And we use this repeated hydrographic data to investigate the variability of this dense water plume. This is what I have been doing before at ABI within these efforts, and we were looking at different types of variability of this plume, but here I will briefly just talk about the internal variability of this plume and a specific case we found, which is depicted in the following plot. So here you have the blue line represents the time evolution of the volume transports of this Weddell Sea bottom water, which composes the core of this dense shelf waters flowing along the slope. And the other lines represent the different density subclasses in which we divided this water mass, being the red line, the subclass which is the less dense, and the purple line representing the subclass which is the densest. The red rectangle here represent equivalent time periods of consecutive years. And as you can see on the blue line, the total volume transports of this Weddell Sea bottom water transported along the continental slope didn't change much between 2018 and 17. However, we measure a clear change in the properties of this deep water plume between both years. Specifically, between April and June 2018, we found that this dense plume flowing along the slope was less dense, warmer, and slightly saltier than the previous year in the same period. And so observation point to these changes, and we want to find out the mechanism behind this, the causes originating this change, right? So we got two main hypotheses. The first one will be that there was a warming of the dense precursors of this Weddell Sea bottom water on the shelf, but this is not matching recent hydrographic data. And our second hypothesis was that these dense precursors, when they cascade down the slope and they entrain warmer ambient waters, they were entraining ambient waters that were warmer than usual, so a less modified warm deep water, this water mass that I mentioned before in the upper part of the water column. So we want to further investigate this mechanism with the help of models, as will be explained a bit later. Here you have different trends that we have been observed by colleagues at ABI of the different water masses in the interior of the Weddell Gyre. In the upper part of the figures, you have a map with the two transects that have been repeated, the repeated hydrographic sections along the years, and from which the data was taken to do these studies in changes and trend. On the left-hand side of the plot, you have the transect corresponding to the meridional one on the right of the map, and on the right-hand side, you have the transect number 2 across the Weddell Gyre. As you can see in both transects, there has been a warming of the widespread warming of the deepest water masses, so the Weddell Sea deep water and the Weddell Sea bottom water. However, the warm deep water that's located above shows contrasting patterns of cooling and warming, and this is quite an interesting behavior we want to further investigate in the near future. So these changes, observational changes, bring us to our scientific motivation. So what we want to do in the future is to investigate if these observed variations and trends in the warm deep water heat content are driven by changes in the intensity and location of the winds over the Weddell Sea, or whether these are due to other processes, like could be an increased advection from the Antarctic circumpolar current, this huge current that Torsten mentioned, that circles Antarctica with warmer waters, or changes in the distribution of the upper ocean stratification. We also intend to investigate how the changes in heat transport pathways and distribution in the warm deep water are followed, and with a special focus on the self-break region for its implications to the variability, interannual variability that I was discussing before, of this dense water plume that follows all along the continental slope in the Western Weddell Sea. For this, our strategy is to employ an ocean model that has been fit to observations. This means that the physics are respected, but also abiding by the observations, which is quite interesting. This has been done in the MIT GCM model with the adjoint method. And we want to employ this adjoint method again to analyze the sensitivity of the warm deep water heat content to different forcings like wind stress and other plausible forcings. We also want to investigate the origins of the heat content changes by looking at the spatial propagation of these adjoint sensitivities traced backward in time in the model. So to finish this presentation, I would just like to highlight the complementary model approaches that we have in this task number 2 of the Work Package 6. So as Mark will present later, he follows the strategy of running sensitivity experiments in which he isolates a specific forcing in a regular forward simulation, and then compares the changes observed with another simulations in which he has all the forcings at work. And so he can attribute the heat and carbon changes to this specific forcing, like wind stress or other plausible forcings. In our case, as I mentioned, we are using an available state estimate, which is an ocean model which has been fit to observations, and employ the adjoint method to investigate the sensitivity of a parameter of interest, like in this case, the warm deep water heat content, to different forcings and control parameters. So that will be all on my side. Thank you for your interest. And if you... Yeah.
Thanks a lot, Pedro, for an excellent presentation, where you sort of clearly make a strong case for why we need to better understand the transport processes. And that brings me over actually to the last presentation before we actually go to the panel discussion. That will be given by Mark Hague. Mark is at ETH Zurich. He's from South Africa, so he was already partly almost in the Southern Ocean from the beginning. It also was the topic of his PhD that he got at the University of Cape Town on the Southern Ocean. And then 2 years ago, he joined my research group at ETH Zurich, working on the Southern Ocean a bit from a larger scale perspective, as you will see in a minute. His move from South Africa to Switzerland allowed him to sort of further explore and even diversify one of his big hobbies and his things he really loves to do, which is climbing the mountains, as you can see in the image. Quite impressive, Mark, what you're doing there. Hopefully, sometimes you hold with both hands on the rock. So definitely spending quite a lot of time in the outdoors, enjoying what Switzerland has to offer in this context. But with that, we jump back into the water, and the floor is yours, Mark.
Thanks a lot, Nikki, for that introduction. Just share my screen. Yes, can you see my screen?
Yes, we hear you well, and we see the screen.
Okay, perfect. Yeah, hi everyone. It's a pleasure today to present a very brief summary of my work here at ETH. So we're kind of going to zoom out a lot now from looking at the Weddell Sea to kind of pan-Antarctic or Southern Ocean perspective. And in particular, we're going to be looking at changes in temperature of the upper 2,000 meters over the last 30 years, and trying to understand why in some regions of the Southern Ocean it's warmed more or less than other regions. But before we do that, I wanted to kind of give an idea of why I'm so interested in this region more from a personal perspective. We've seen why the Southern Ocean is so important for global climate, but I wanted to kind of briefly talk about personally why I find it such a fascinating place to work in. So as Nikki mentioned, I studied at University of Cape Town, which I'm showing here in the red dots, and you see this we're right on the doorstep of the Southern Ocean. And so during my undergraduate, there was, of course, quite a lot of a focus on this region. And it really captured my imagination, this really remote, harsh region, which is also poorly understood and has very complex dynamics. Kind of trying to capture here with this snapshot of the currents. So you see these very strong eddying field. You have also the interaction with sea ice, which is a big part of my previous research and is also important here as well. So that's kind of my own perspective, but I wanted to now jump into trying to understand how the Southern Ocean has warmed over the past 30 years. So I'm going to show an animation. Hopefully it works. Yes. So what you're looking at here is the mean warming in the, so from 2,000 meters to 250 meters. So we're excluding the kind of warming in the surface. So it's really this deeper layer, which responds on longer time scales. And this is taken from an ocean reanalysis model, which tries to kind of capture the observed changes in the ocean interior. So each kind of frame is a monthly anomaly from that frame to 1980. So we're basically in red, of course, seeing regions where the ocean is warmed, and in blue regions where it's basically cooling. So I'll just hopefully play it again, so I can talk you through the kind of patterns that we see. So basically we see already in the 80s that this warming in the Atlantic and in the kind of Agulhas return current is a bit more pronounced, and the warming in the Pacific is a bit slower. You see also, of course, large-scale cooling actually happening. Then you start to see this warming in the Weddell Sea and also in the Ross Seas. But basically, the overall kind of point I wanted to make here is this strong kind of regional effect where you have really much stronger warming in the northern part of the Atlantic basin and also in the Indian basin, but actually you see this to a lesser degree in the Pacific basin. And also you see also those differences also happening in the high latitudes. So this kind of contrasting warming and cooling that's already been mentioned in the Weddell Sea. So the approach that we take here to try to understand these kind of patterns is using an ocean model. It's a regional model of the Southern Ocean with an open northern boundary. We run a so-called hindcast, so very similar to the reanalysis that I showed previously. It's trying to simulate kind of the historical conditions over the past 40 years or so. It's an ocean-only model, so in order to capture effects happening in the atmosphere, we use this Era 5 reanalysis product. And so we basically prescribe the changes in heat fluxes at the surface, freshwater fluxes, including ones originating from sea ice changes, and of course changes in the winds. The model is at a 1/4 degree resolution, so you could say this is eddy permitting, but not eddy resolving. So it's a kind of medium resolution model. So moving on to kind of the main results that I want to highlight today from the model. So here I'm showing the changes in ocean heat content over the top 2,000 meters. So this is basically the change over this 30-year period. So we look at the the mean ocean heat content in the 2010s, and we subtract from that the mean ocean heat content in the 1980s. And we get this pattern of warming and cooling. Again, just to highlight, this is integrated over the top 2,000 meters. So here we see what I'm referring to as these kind of zonal asymmetries. So that's basically if you follow a line of latitude, so say 40 degrees south, you see kind of contrasting patterns of either warming and cooling or stronger warming and less strong warming. So if we focus on this most northerly region, we see again, as we saw before, this pronounced warming in the Atlantic and Pacific basins, but actually a slight cooling in the Indian basin. I won't go over all the kind of intricacies of these patterns here, but the main point is that if you take a zonal integral that's shown in the bottom here, so if you just add all of this, these patterns up, you kind of miss quite a lot of the variability. And this approach is very useful, that taking this kind of zonal mean perspective or zonal integrated perspective is very useful, but it's important to also recognize that you mask out a lot of variability in this way. So taking a step further to try to understand where do these zonal asymmetries come from, basically what we've done is, as Pedro nicely introduced already, I'm separating, trying to isolate the effect of changes in wind stress over this 40-year period, the different changes in heat flux, and also the changes in the freshwater flux. So we basically decompose this total signal that's shown here on the left into these different components to understand really what are the mechanisms which lead to such a pattern. So here I'm just kind of summarizing those results. So what I'm showing here is 3 different regions which correspond to the regions kind of separated by these black contours. So you have the high latitude region dominated by sea ice, the Antarctic circumpolar current region, the ACC, and to the north of that. So that's what's shown here. And really the important point here is these different shadings that I have here. So they indicate the different basins that are separated here by these straight lines. And if you look at the blue bars, that's the experiment where all the forcings are varying simultaneously. And straight away you can see, for example, here north of the ACC, the total change is completely dominated by only 2 basins that we already talked about. That's the Pacific and the Atlantic basin. And you see this kind of asymmetry in all 3 regions. But the important point that I wanted to make here is that this asymmetry extends into the experiments where you have only 1 forcing. So for example, if you just, it's not really important which basin it is, or it's more that the width of these different shaded bars is varying actually quite a lot in all the different experiments. And that suggests that actually a lot of this asymmetry is coming from actually asymmetries in the forcing themselves. So for example, the winds are maybe stronger in the Pacific, and this is leading to a different response in the Pacific to the wind stress changes than in the other basins. And so just to try to summarize quickly, we've found that there's been kind of varying patterns of warming in different regions, leading to the so-called zonal asymmetry. We used an ocean model to investigate the drivers of this. Of course, I haven't been able to go into really the details. I'm just giving some an overview, hopefully, to get you interested. And then we kind of decomposed this total change into these different components to try to get at these drivers. Okay, thank you. So with that, I'll hand back over to Nikki to lead our discussion.
Okay, thanks again, Mark, also for giving a wonderful perspective across the Southern Ocean. Before I start the panel discussion, I would like to give the floor to Griffiths for a quick update on how we proceed from here onward.
Hi, everyone. First of all, thanks to all of our presenters for their very detailed presentations. That was all very fascinating. I wanted to just quickly remind everyone we have hit the 1 hour mark here, but we budgeted 90 minutes in total. So I think we still have some time for our panel discussion. I just want to remind all of our attendees to please put your questions into the chat if you'd like to ask anything to any of the panelists. And otherwise, we'll try and wrap up somewhere in the next 20 to 30 minutes. And with that, I'll give it back over to Nicolas.
Yep, thanks a lot. Yes, and please use the chat for really looking forward to your questions. I think because, yeah, the more interactive this is, the more interesting I think it is for everyone, including the audience. What I'd like to do next is to start a little bit of a discussion, maybe also a lead into the discussion with everyone attending, but maybe start with the first question in a most general sense, and it is mostly geared towards Torsten, Pedro, and Krissy. Because, I mean, you're focusing a lot of your work on the Weddell Sea, and I think you've given some indications why the Weddell Sea is interesting. But you kind of wonder, what about the other regions in the Southern Ocean, such as the Ross Sea? So why is the Weddell Sea so distinct from the Ross Sea, and how can we put the Weddell Sea a bit in the larger scale context? Not sure who is willing to jump on the question first, but I think it would be just good to know that, because Mark talked about this asymmetries. So yes, I mean, maybe there's asymmetries not just further north, but also around the continent, and why this is relevant.
Okay, so I guess the research that has been going on in the Weddell Sea has I guess a long history, and I think one of the fascinations is that the Weddell Sea has been producing basically the densest bottom water, for instance, so displaying a very important role in that context. But of course, there are many similarities to the Ross Sea. What makes the Weddell Sea fascinating certainly is that there have been long-standing observational records which are available, and there are dedicated programs trying to use somehow scale resolving observations like the Argo floats that Krissy showed, but also monitoring of the boundary currents and connecting actually the gyres to the shelves, which is also work that's going on in the Ross Sea. But I think in terms of data sets available, I think it's an outstanding region, and for that perspective, it's also a good study object when it comes to how does upwelling and shelf processes and ice shelf melt interact.
Krissy or Pedro, you want to add something?
Maybe
you can make a case why we should study the Ross Sea as well. But I
agree with.
Try to put it a little bit in perspective. So what makes?
Yeah, I agree with Torsten that the availability of observations along decades is quite useful and interesting in the Weddell Sea and marks a difference. But also I would like to add that this area forms the largest amount of Antarctic bottom water, which we all know fills the bottom of the oceans and starts this thermal circulation, this meridional overturning circulation in the southern hemisphere. So it will be the Weddell Sea, and particularly this dense plume that flows along the slope, and part of it escapes through the deep passages. It will be the main contributor to Antarctic bottom water in the global ocean. So it's something quite interesting with regards to climate and ocean circulation. Yeah.
Krissy?
Yeah, I'd also say from an Argo float perspective, there, like Torsten said, there's this rich history in the Weddell Sea of observations, and also the where the ship goes is where we can deploy the Argo floats. So again, we have a lot more data from Argo floats in the Weddell Gyre as well, simply because the ship has been going there every year for years. But the Ross Gyre is getting there. It's really increasing in its observations available. And I would argue that actually what we really could do with is looking at the Weddell and Ross gyres together, even possibly viewing them as a connected system and trying to understand it in that perspective, which is why research like the research Mark was just presenting is so important.
Thanks.
Maybe in this
Please go ahead. Yes.
Context as well. I mean, what we know is that around Antarctica, the freshwater, the meltwater that's coming from the continents has been increasing, and we have a downstream effect of this freshening. So aspects that I guess happen in the Ross Sea in terms of meltwater production, they don't stay there. They head downstream, and that occurs in other regions too. And so we can't look at these gyre systems in isolation, because they are connected also by a boundary current system that transports properties from one to the next. And so if you want to understand the causes for depletion of bottom waters, you have to look at the whole system. That's certainly worth considering.
Yeah, but I totally agree. I mean, but I think the argument about observational is having observations in place is a huge plus, and I think it's thanks to decades of observation, primarily from AVI and other institutions, that have provided that background. Sort of another thing that occurred to me as I was listening to you was you didn't talk too much about the anthropogenic perturbation. So you talk, I mean, Torsten, you talked at the beginning, okay, well, the Southern Ocean is sucking up so much heat, 75%, but then neither Pedro nor Krissy, you kind of talked about the changes you're observing in the deep Weddell Sea to be connected to that heat uptake. Did I miss something, or do we don't know, or what's the situation? Maybe Krissy, you first.
Well, the simple answer for me is that so far, with the heat budget work I was looking at, I'm looking at the mean state. I've taken all available data and tried to get a big picture perspective of how heat is getting moved in the first place, because it's really important to understand that big picture mean state in order to draw out the changes. And so at this stage, I've been focusing on that, but the what's next part for me is to look at these changes and to try and understand these long-term changes in context of that big picture. So that's why I didn't address that, is simply because it hasn't been the focus so far.
And you, Pedro? So
yeah, in my case, similarly, I have been focusing so far in the interannual variability and seasonal variability of this dense water plume, but didn't look yet too much at the trends. So I didn't mention much on that regarding the plume, and I did mention briefly about these trends that have been observed by colleagues at AVI in the interior water masses of the Weddell gyre, in which they found a clear widespread warming in the deep waters, in Weddell Sea deep water and Weddell Sea bottom water, and contrasting patterns of cooling and warming in the upper layer with the warm deep water. And this is what we want to further investigate and maybe try to tease out the mechanism behind that, and probably a change in the westerly winds, poleward migration or intensification, changes in the geographic areas where these winds drag the ocean, the surface ocean, right, will be probably an important factor on that. But this is on our near future investigations.
Yeah, that brings me over to Mark. I mean, a major focus of your work is to kind of separate the different components: freshwater, wind, forcing, circulation changes in response to that. So if you were to ask, okay, well, what is that 75% that we always hear? Is that what you see or what you don't see? So can you put this a bit in the context? And then the second follow-up question would be to connect your work a little bit more with what's happening in the WEDL-C. Can you say something about these questions already, or is it too premature?
No, I could make some comments. I think the 75% is on a bit of a longer time scale, so that's more on the 100-year time scale, whereas I'm on this kind of shorter 30-year time scale. In that case, I find more of a equal role, let's say, for changes in winds and changes in surface heat uptake, which I think is in agreement with previous work as well. So we have a redistribution of the heat that's driven by the winds. So that doesn't necessarily represent heat that's actually being removed from the atmosphere. It's more that kind of where the distribution of heat is being changed. But still, it makes a significant part of the total. In terms of the WEDL-C, I didn't show in detail those results here, but there are quite interesting changes that I see in my model in the WEDL-C, and it's kind of, again, actually the heat flux is a very minor role here, but the winds and the freshwater flux are both important contributors that kind of work in opposite directions. So we have actually cooling driven by largely by freshening of the surface ocean coming from sea ice changes, and then warming from the winds. It seems the changes are quite complex, and I haven't really been able to in detail understand how this actually occurs, but it's definitely could be an interesting topic for future work and collaboration in the work package.
Maybe just for the audience, you mentioned the cooling that comes from the freshwater input. Could you quickly explain how that works?
Yeah, as I said, I haven't understood in detail, but it seems to actually be driven by circulation changes in the Weddell Gyre itself. So I actually have, it appears based on a preliminary investigation that I have less of this. I mean, Krissy talked a bit about this warmer waters that come from the north, mainly in the eastern part of the gyre, that I kind of have just less of this warm water being brought in, and that's, again, I've isolated this is driven purely by freshwater changes. So yeah, that's ongoing work. Yeah.
Okay. Just since I have you on the line right now, there's one question coming from the audience.
Sure.
First of all, congratulations to everyone for amazing talks. Something I'll second in a minute. The question is, how well is your model reproducing the observed variations that you showed at the beginning?
Yeah, so at the large scale, it's pretty good. So we get this accumulation of heat north of the ACC that's in the observational record. Then there's this kind of cooling in the Pacific that is also seen in the observations that we are also able to capture. That's in the kind of ACC region, so about sort of 50 south. This is a bit overemphasized in the model, but again, this general pattern is captured. If we go then to the sea ice sector, there we have kind of, again, the large scale patterns are fairly well captured, but of course we have biases as in any model. But
no model is perfect.
No model is perfect.
Okay, I would like to move to the third topic I would like to touch upon, and that's the role of small scale processes, mixing, role of turbulence, eddies, etc. So Krissy, I mean, you highlighted essentially the important role of vertical mixing as a way to transport heat from the intermediate waters more towards the surface. So could you explain a little bit what drives that mixing, and what's that? Is that eddy driven mixing, or is it what is it? And because depending on your answer, we might have this in our models or we might not have. My suspicion is we don't. So can you explain a little bit?
Well, with the approach that I've taken with the heat budget, it's a little bit tricky because we're looking at the large scale picture. I've had to cut out the surface layer. So really, when you do a heat budget, you want a uniform volume of water, and usually sort of integrate it to the surface or for the full ocean depth. We've had to really focus on a layer of water representing the warm deep water, that heat source water mass to the ocean. And so we had to be really selective about how we define the vertical boundaries of this layer of water. And we defined it as the midpoint of the thermocline. So this way, we always ensure that we include the sort of the core of that warm deep water, but always exclude the overlying surface waters. And so then you have this really, at the upper boundary, you have this temperature gradient from the warm water within to the cold water overlying that. And so naturally, where you have a temperature gradient, you have a transfer of temperature in that, or heat in the direction from lots of heat to less heat, right? And so we sort of parameterize this component using a diffusivity value that search through the internet through not the internet, the literature, sorry, to help us to represent the turbulent mixing component in the vertical. And this, in that figure, I showed the little blue circles showing the upwards movement of heat through the thermocline. And this actually happens uniformly throughout, but in that particular area, based on the analysis that we did with the Hague floats, it seems to be that's a rather large balancing term for removing the heat that is otherwise going to build up in that area. And so one of the major points where we need to improve our work is to get adequate estimates of diffusivity in both vertical and horizontal, I should say. Horizontal is a little bit different because we've updated that now thanks to a new paper that's out by Florian Sevelik et al. They used Hague floats to actually derive horizontal diffusivities and provided a global data set of that, and we incorporated that into this analysis. But for the vertical terms, we're really missing that information, and for both actually we're really missing that information within the Weddell Gyre itself. So this is a bit of a data gap, and this is actually something that Pedro is going to be working on with it using a joint modeling. So that's going to be really useful, and this is the benefit of really putting together observational and modeling efforts to really try and answer these key critical gaps in our knowledge. I hope that answers your question a bit.
I think you just played the ball over to Pedro.
Sorry.
Yeah, regarding that, we recently learned that there's a paper by people running this state estimate in GPL, the ECO4, in which they recently estimated these diffusivity parameters both in the vertical and in the horizontal for the whole world. So it's a global estimation with different values for different regions, and this is something that we should talk about that, and could be useful for your endeavors actually, and already available. So yeah, it's a paper by Gael Forget et al.
Okay, no, I think this is super interesting. But coming back, but what drives that mixing? I mean, have an idea? Maybe Torsten could chime in.
Yeah, so basically we are not resolving the processes that drive that mixing in the analysis that Krissy does. We are working from annual mean properties, but since these are properties or processes that happen below the mixed layer, I guess there will be effects related to internal waves, internal wave breaking, that might be responsible. In areas on the shelves, of course, the processes might be different with the interaction of the bottom In the shelf seas, we have wintertime convection reaching down till the seafloor. So there we have really a winter, say, cooling and sea ice formation driven mixing that erodes the whole heat of the water column. But in the weather gyre interior, I think we are not resolving these. But I guess the processes like internal waves and internal wave driven mixing, maybe it's nothing you have explicitly in your model, I guess. But there are formulations where basically one can plug in one-dimensional representations of internal wave-driven mixing in order to resolve this process. And I think what we should be concentrating on is also looking into the seasonal evolution of the mixed layer in terms of entrainment processes. That is something we could do. We have not quantified, but Krissy pointed to me to a recent, or not to quite an old paper from Peter Schlosser, I think, from the 1980s, where they actually showed that this had quite a strong role in the close to the tip of the Antarctic Peninsula. Estimated for also indirectly using tracers. So there's some information out there, but I think from the data we have, we could make a better job into looking into the seasonal evolution and infer some mixing processes along that way.
Yeah. Going from the vertical to the horizontal marker, you mentioned that using a quarter-degree model for your analysis, and so it's eddy permitting, but not quite eddy resolving, or fully eddy resolving, certainly not the highest latitudes. So are you worried?
Yeah, I think this is definitely a caveat to the study, that we might be missing this eddy transport or role of eddies. Yeah, it's really an open question, and I think it's reassuring that the model does capture the large-scale circulation quite well. So we do get this subduction of mode and intermediate waters that Torsten talked about. And at the high latitudes, I didn't mention it, but we're using a terrain following vertical coordinates. So we capture quite well the this like bottom water formation, for example, and interaction with the ACC with the sea floor is quite well represented. So I think, of course, it's a limitation, but it's also very expensive to run these very high resolution models. So this is why I would take a more larger scale perspective, and maybe at the regional scale, we would have less confidence, I think, with the results.
Well, there's definitely a space for further improvement along all these subgrid scale processes that we're just kind of scrapping at the surface with the tools that we have available to us. Okay, I think maybe from a quick statement from each of you towards the end, and maybe the audience can think of further questions in the meantime. So looking a bit into the future, so where would you expect, and you're happy to speculate, where would you expect the biggest changes to occur, and why, as concerning ocean and carbon heat uptake in the Southern Ocean? Are you, just an example, are you worried about changes in the winds? Are you worried about changes in sea ice? Or do we see a sort of a collapse of deep water formation? I'm just giving you examples. I mean, so maybe Krissy, what do you think about the future, the things that could really be the big change in the Southern Ocean that we should watch out for, that we kind of, maybe the big known unknowns?
That's a big question.
You can speculate.
Well, So I guess one of the, when you look at timescales, one of the most sort of powerful, rapid changes that can occur is in the winds, right? So the influence of the winds on the circulation and the sea ice as well, I think, and the ocean circulation, of course. I think the understanding the role of the winds on ocean circulation in particular is a very interesting and powerful component that we need to understand.
Okay, thanks. We'll continue with Pedro.
Yeah, I agree with Krissy that wind will be a key factor on this, and we know wind is related not only to ocean circulation but also with the transport of sea ice in surface, which will enhance further sea ice formation, for example, in the southwestern Weddell Sea, which will at the same time interact with the formation of the dense and bottom waters. So everything is related, and yeah, I think the winds will play a key role here, but all the different mechanisms are somehow interrelated, so it's quite difficult to say which one will be the most relevant, but there's also some work done by colleagues at ABI with other international colleagues in which they are looking at tipping points in, for example, the Filzner ice shelf, which is a dense cold ice shelf in regards with the waters that are just in front of the ice wall or the ice cliffs, and so they protect this ice shelf from the incoming warmer subsurface water, the warm deep water that we were mentioning before. And well, there are some model simulations in which with appropriate future expected scenarios of warming and forward migration of the winds, this stability can be flipped over, and then we can have an intrusion of warmer waters melting faster these ice shelves, and then of course influencing the density of this very dense bottom waters form, which will be unable to mix in the same way with the ambient waters and capture their heat and carbon. So it's something very fascinating system, interconnected, and it's hard to give a clear a clear mechanism behind. Yeah.
Okay, we heard wind, we heard also some ice sheet instabilities connected to ocean circulation. Mark, where would you put the finger?
Yeah, I think there was a recent paper actually by J.B. Saleh, who is the overall PI of SO-CHIC, looking at long-term changes in stratification globally. And the Southern Ocean came out as one of the regions with really very strong trends in stratification. So kind of shoaling of the mixed layer or increased vertical density changes. And I think this could have a big role to play for the storage of heat and carbon, particularly in these mode and intermediate waters. So I think we need to understand more the role of stratification in kind of limiting how much heat and carbon ends up in the deep ocean, and that and of course you have changes in winds which may go against the heating from the atmosphere, which enhances stratification. So which process ends up winning out in the future, I think could have major implications.
Cool. Torsten?
Yeah, I think I can be heard. So I think many of the important elements have already been mentioned, but I think maybe in the light of the findings that Tilla Roy and co-authors have achieved, where they basically not only looked into these feedbacks influencing the efficiency by which carbon is taken up by the Southern Ocean, but they did it in a water mass specific way, and they also beyond quantifying time or model mean values, they also looked into the uncertainties. And I think where these models show the large uncertainties, I think it's certainly worth looking into. That relates to, say, the outcrop areas of water masses for outgassing and uptake of carbon. But that also relates to the circulation strength of the upper overturning cell of the Southern Ocean seems to be quite a strong sensitivity there. So that and then there is the aspect of, I guess, regional changes that come out of Mark's work, but also out of your own work, Niki, I guess, when it comes to these strong trends that the carbon sink can have. Yeah, I think I don't have a conclusive answer for you, but it's certainly worth being kind of guided by these large, by looking into where the spread of the models is large, to distinguish what kind of basic physical knowledge gap we have in these areas.
Okay, super. Then thanks a lot to everyone. A big hand. The audience is applauding too. And with that, I would like to close this session and would like to hand over to Griffith for the final word.
Thank you very much. I'd like to also thank all of the speakers and panelists, Torsten, Pedro, Mark, Krissy, and of course, Nicolas for his excellent moderation. Thank you for all of your preparation in participating in this webinar. So I just want to remind everybody that the recording of this webinar will be available on the SO-CHIC YouTube channel. We will also be collecting all of the presentations for dissemination. And I also want to flag the next work package. Work package 5 will be coming next due to some scheduling issues on January 31st. So you can find out more information about that through our social media channels and our website. So thanks once more. We kept time very well, and more work to be done, but obviously very good research so far. So thank you, one and all.
Thank you.
Bye, everyone.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.